Can you imagine humans giving birth to babies the size of sand grains? Such a size difference between adults and babies sounds totally bizarre, but it is the norm for algae, or seaweeds. Algae begin their life as spores that are about 1/10 of the size of the period at the end of this sentence. From such humble beginnings, algae can grow to hundreds of feet tall, the size of a small redwood tree. How is it that the success of something that can become so large depends on something so small and seemingly fragile?
The answer may lie in the physics of the waves that bash against these spores. I want to see if avoiding the physical forces of waves can explain why these algal spores are so small. Perhaps if we as humans had to live here, cemented on the rocks in the intertidal, we would have to produce offspring just as tiny.
My name is Kevin Miklasz, and my research revolves around the weirdest, strangest parts of the natural world I can find.
I try to combine physics with biology to understand the more counterintuitive aspects of the world. Often what is bizarre at first sight is actually necessary for survival. We just need to find the right questions to ask.
Imagine yourself living in a place hit by tornadoes every day. The algae that I study have waves as one of their biggest enemies. They live in some of the harshest, wavy environments on the planet. We have recorded water velocities in the intertidal of up to 32 meters per second. That generates the same types of forces that we'd experience in tornado-level winds. These forces are not an infrequent occurrence like tornadoes, but they hit the organisms on our coastline almost every day. I was intrigued to understand how they can survive in these conditions. How fast do spores attach to surfaces? What sorts of glues do they use to attach? How quickly do the glues set, and what sorts of attachment strengths do these glues have? Understanding all of these elements allows me to understand the big question. Will spores be knocked off the rocks by the physical forces of waves before they have time to settle?
The small size of algal spores allows them to hunker down really close to the surface and live in something called the boundary layer, or a region where the water velocities and forces are greatly reduced. Thus, the bizarre minuteness of algae can potentially be explained by physics. Namely, this can be a way for the spores to avoid the full impact of a wave.
To test this hypothesis, I need to measure how well algal spores can stay attached to surfaces after being blasted by the types of forces they experience in a wavy environment.
I put my creativity into action and created a device called the shear flume to answer this question. This device recreates a type of forces, called shear forces for the physics nerds out there, that these spores are likely to feel in the boundary layer.
This allows me to test how adapted the spores are to withstanding these types of forces. I can let spores settle for different amounts of time on the surface, allowing them to become more attached before I test them in the shear flume.
I let spores settle on this little mount right here. So I can put this in the end of the shear flume here, so that when the water rushes past here, it rushes over the spores, and I can see what kind of forces it takes to detach the spores from this little mount.
In this way, I can measure both how fast and how strong spores attach to rocks. I found out that spores could attach to surfaces extremely quickly, meaning that their glues took an exceptionally short time to set.
When the glues set, which only seems to take a minute or two, the glues are exceptionally strong, meaning the spores are able to withstand even the strongest forces that they would experience. The one complicating factor is that the spores don't always use their glue right away. They can wait up to several hours before even putting down the first bit of glue, meaning that even a modest little wave would knock them right off the rocks, though it probably wouldn't destroy them.
Be yourself a scientist. Build your own projects and share the answers for my challenges in the Curiosity Machine.
Stay curious.